Great. So first of all, thank you for inviting me to give this talk. I'm really happy. It's a delight to be part of Women in Science, and we already had one nice talk today. So today I'm going to talk you through our work and our plans in PhenoRob and doing agriculture from a more robotics perspective. So I would just like to acknowledge my PhD students who started with me in my research group recently, Liren and Julius. So they're here on the call, and thanks so much for the contributions. So I want to start as a roboticist, our vision about the role of robots in agriculture. So robots are intelligent devices, and increasingly we have new methods of artificial intelligence, especially deep learning. And so it's relevant to think about the spectrum of autonomy and how robots can contribute here on different levels. So on the lowest level of autonomy, everything is done manually. So robots don't play any particular role. So humans are doing all the data collection, all the operations on the field, for example, applying fertilizer, weeding, etc. And then if we go up a little bit, humans are using robots, but in a very manual way. So here the robots are performing some tasks in order to replace conventional machines. So for example, these are the types of tasks we typically do in PhenoRob, such as flying drones using a joystick or using some kind of app to plan missions and collect data. So this is what we mostly use in PhenoRob and also in general in agricultural robotics. So looking at one level higher even, we target the level of autonomy in our work that's even above that. So instead of using robots to replace the current methods on a one-to-one mapping, we want to challenge existing approaches and really exploit the fact that robots are getting more autonomous. So we want to try to program them to make their own informed decisions and reason about the field and even cooperate in new workflows. So this way, the robots are operating fully autonomously, making decisions on their own and with minimal human interactions. So, but in order for this vision to come true, we need new robotic algorithms allowing us to interpret different features of the field and make the actual decisions. So here's some types of decision-making scenarios that we consider in a very intuitive and basic way. So these are some examples where the robot needs to think about their own state and the state of the environment and which would be the best possible choice with respect to those constraints. So to make this more specific, in this talk, we're going to consider mostly monitoring a field with one UAV, just to make the problem a bit more specific and manageable. And this is where we did a lot of prior work as well. So here we have a single UAV or a drone that is flying at different altitudes, trying to collect data about the field. So on this picture, we can see a top-down view of the UAV, in two-dimensional view, and the task is to survey specific characteristics in this area. So following a conventional approach on the second layer of this autonomy spectrum, we can create a simple lawnmower zigzag type path at a fixed altitude, given the limited battery life of the UAV. So this is simple, fast, and also this is what we have available in most commercial products. However, what if we have certain parts of the region on the field that need to be inspected more closely? So some use cases could be, for example, we want to try to find very accurately the weeds on the farm and distinguish with respect to crops, or we want to identify particular locations where the plants are sick and have diseases and study them more closely to figure out where it went wrong. And I put also these 3 dots here because to emphasize that this is an area that we're still exploring potential use cases. So the major drawback of using this lawnmower type path is that the entire environment is mapped with a constant resolution. And this is something that we define before the UAV actually goes on the field. So because we don't know where the areas of interest or these anomalies are, and then we can't focus on mapping them adaptively more closely to improve accuracy in these areas. So using a decision-making approach, what we actually do is try to perform more efficient and targeted monitoring by allowing the robot to make choices, so to decide where to go next. This way, we can adaptively focus on collecting more and higher quality data in these more interesting areas, leading to a much greater efficiency of the mission and better use of the limited battery life. However, in order to achieve this level of autonomy, there are several challenges. So first, we need to decide, how do we actually model the environment, and how can we define an objective that tells us how useful future measurements are? Second, we need a planning algorithm that balances between exploring the unknown field initially and exploiting regions of interest as they are discovered. It also needs to be able to generate paths that satisfy the robot dynamic and endurance constraints, for example, battery life limitations. And also, if we want to replan from time to time in order to achieve adaptive mapping, we need to make sure our algorithm is actually computationally fast enough in order to run on board and online. And finally, a key aspect of both mapping and planning modules is that we need a reliable model of the sensor. So this could be, for example, the camera equipped by the drone that's pointing downwards and used to take measurement. This model is very important because we use it to define how useful measurements in the future are in a predictive way, and also we use it to update our actual map, as we will see later. So if we think about the problem of aerial imaging, important trade-off lies in the fact that our UAV can actually see the same point on the field at different altitudes. So the resolution of the image will be different spatially. And so we need a sensor model that actually accounts for this multi-resolution aspects, and also changes uncertainty, because we would expect that when we reduce altitude and go lower to inspect the plants, we are more certain in the measurements that we obtain. This makes our decision-making problem very complex and also computationally challenging to solve, especially if we want to do it online. These three elements form the foundation of our research work here in Finorob. So our goal is to develop frameworks to address the challenges associated with decision-making in uncertain 3D environments and also on computationally limited systems. So by using these algorithms, we can really push the boundaries of autonomy in agriculture and ascend the scale that we saw before of robot autonomy. So in this talk, we focus on this application of UAV-based terrain monitoring, but the methods I present, we can later think about how to generalize them to different sensors and also different actions performed by the robot. So now that we have an idea of these three elements that we need to build our decision-making framework, let's try to assemble them together in a robot system. So working step by step. We have a robot that's equipped with a sensor, for example, a depth camera or a multispectral camera or a thermal camera, which we use to extract measurements from. And then we use these measurements to build a field map of the environment of interest. So here we might have some prior information, for example, from previous missions that we used to support the map initially. And then we have a planning algorithm that uses these maps to optimize actions or trajectories based on the mission objective. So for example, we want to collect data efficiently. This would be our objective. And this way we close the loop between perceiving and actually acting. So we use the map in order to make informed decisions. The key ingredient here is this utility function in pink, which is used to reflect the aim of the mission, such as efficient data gathering. And this is what we want the robot to do or what we want it to sense. We use this definition of utility in order to measure how valuable are future actions. So this is all we need in order to build a decision-making framework for our robot. So next, I want to talk you through some of the methods of our previous work that we actually developed in each of these modules. So first we start with the mapping part and how we can actually create a consistent field map using the measurements that we obtain from the robot. So if we think about agricultural fields, there are many challenges associated with mapping such an environment. So usually we have large field areas that we want to monitor, but we also have robot cameras that provide increasingly high resolution images. Also, if we're doing some kind of processing or interpretation of the images, such as using a deep learning model to find the weeds and crops. So this would be an example where our model has actually identified the red weeds and the green crops. We need to make sure that such a model is actually imperfect and there might be some uncertainty that we want to include in our mapping strategy. So the main challenge in mapping is how can we incorporate all of these elements in a single, compact, and probabilistic map that we can then use for planning. This is very different to taking many measurements of a field and putting them together later, because we also want to update our map online in an efficient way as new measurements are received. So I'll present very briefly a mapping method that we developed during my PhD time that addresses these issues. So specifically, we designed a strategy for mapping continuous variables, for example, temperature or vegetation cover on a terrain. And we developed an approach that directly caters for the needs of fusing dense visual imagery, accounting for altitude-dependent behavior that we saw on this picture where the UAV was able to take on different altitudes, but also at very different spatial resolutions. So our mapping strategy is based on a Gaussian process model, which is commonly used in environmental monitoring. And this is a machine learning technique, which basically allows us to capture the correlations in the environment. So if we have plants that grow very closely to each other, we would use a Gaussian process in order to capture how information about one area of the field influences another. And we then use this model as a prior for fusing new measurements as they are received. So this is just kind of mathematical formulation, but for more information, I put the reference on the bottom. The key takeaway is that by using such an approach, we have a fixed resolution map, as we saw on the previous slide. And so we don't accumulate new measurements over time. Instead, we specify which resolution we want to do the mapping at, and we're able to update portions of the map corresponding to new measurements. And this is very important for real-time and online applications. The ability to use a previous map up to a particular point, take new measurements, and put them together using this Bayesian fusion step over there. And using such an approach, with the Bayesian strategy, we can also consider measurements at different resolutions and uncertainty, which is exactly what we want. As we said, if we use sensors such as the weed detection module that we saw previously. So this is some of the work that we did before, and what we're currently looking at is trying to use some information about the field in order to adjust our mapping strategy. So if we go back to our field and we look at very closely on a very fine scale what's happening, we have a fixed resolution map, as we said, that doesn't really reflect the uneven distribution of plants on the field. So our idea now is to use adaptive resolution methods in order to adjust the resolution of the map based on what we see in the images. So here's an example where if we have very high detail in the images and plants growing very finely in clusters, we want a very high resolution on our map. And where not much is going on, for example, we just see soil, then we have low detail and we can essentially cluster these large areas together in our map in a very coarse resolution. So this is just some work that's currently in progress. So that's it for mapping. So moving on to the planning part, how can we actually use such maps in order to find optimal paths for a robot to execute missions? So as we said here, the main challenge is how do we quickly find useful paths in a nonlinear and very high-dimensional problem space? So especially if we have a UAV moving in 3 dimensions and some very funky behavior of our sensor, it's very not trivial to solve. So we need a new and computationally efficient algorithm suitable for online planning with the computational constraints of the real robots. So here, again, referring to some previous work during my PhD, we developed an algorithm that does this. So just to talk us through it, we developed finite horizon approach, where we basically try to, after a certain amount of time, generate smooth trajectories for a UAV to follow. So it alternates between replanning and then executing that plan until we exhaust the budget or we run out of battery. So in the replanning, we have two steps. So first, we consider a very coarse search of the optimization space. So we look at different points in the environment and we try to figure out which are promising for the UAV to visit. And this is done on a very coarse scale because of the computational complexity, as we said, associated with performing an exhaustive search. So to evaluate trajectories, we use our sensor model to simulate what measurements we would to get if we were to execute a particular path. So, for example, if we have measurements that were on a location that we haven't been yet, that reduce the uncertainty of the model, these would be quite promising to visit in the future. So we develop a mathematical formulation that essentially captures the gain and the value that we would obtain were we to obtain particular measurements along a path. And then we use this very coarse solution in order to refine it using an optimization routine. This is, in our particular work, we considered an evolutionary optimization strategy. But the main idea is to actually use this core solution and then try to improve it using an optimization routine. And again, the way we evaluate or how we compare different trajectories in this approach is we look at what is the gain or the utility of the measurements that we get in the UAV-based terrain monitoring scenario. So why would we want to do this? So first, considering smooth trajectories actually allows the robot to execute trajectories in a dynamically feasible way. This is very different to as if we were just looking at the points individually and then executing very jagged maneuvers that are hard to follow on a real robot. And secondly, as we already hinted, a key feature is actually using the coarse optimization solution in order to initialize the optimization routine later. So usually what we do when we consider evolutionary optimization is we initialize in a random way. But here we try to use this output of the grid search, even though it's imperfect, in order to get a better solution quicker and to converge quicker on a good solution. And secondly, looking at the planning approach as a whole, that's finally, by using this fixed horizon alternating between replanning and plan execution, we can actually take into account new measurements as we obtain them during the mission. And this is what we call an adaptive strategy. If we use measurements during the mission in order to tune our path and tailor it as to where we should collect more information. So for example, if we saw one of these disease parts of the field, what we can do with this strategy is adjust new plans so that we take that information into account and inspect this area more closely. So again, this was something, this was a strategy that we developed previously, and in follow-up work in FINAROB, what we're actually looking at is improving the efficiency of this approach. So one bottleneck that we noticed when we tried to run these algorithms on real robots is that predicting measurements is a very complicated task and it takes a lot of time. And if we want to create very good plans where our optimization has good high values, we need to simulate many possible futures and evaluate them. And this can be very computationally expensive, especially if we have many of them and each of them are very complex. So we're trying to isolate this part of the algorithm and see how we can do better. So one idea that we had is actually learning the value of future objectives in a simulation environment and using them for planning based on a trained model. So here we see one of the simulation environments that we actually work with in order to evaluate all of our algorithms before we go into the field and run them on our robots. And again, this is just some work and some ideas in progress. So putting everything together, I just want to show some results that we got previously. So typically what we do with these algorithms is we start with simulation environments, such as the one that we saw on the previous slide, and then we evaluate them against different benchmarks. So here we compare different strategies. So the coverage planner that we saw at the very beginning of the talk, just random motion, and also the rapidly information gathering tree, which is a state-of-the-art informative planner. And in our evaluation, we look at how the different information metrics, so uncertainty of the map and the error of the measurements, evolved during the mission. So looking at the red curve, this is kind of evidence that using our approach with the two-step optimization routine, we obtained the fastest reductions in both uncertainty and error with respect to the map. And then as a step towards real-world deployment, we validated the approach and integrated the whole system in photorealistic simulated environment. So we took a publicly available data set consisting of lake imagery. It's called RIT18. And this is we use as a ground truth, so we know the classifications of all the different features on the orthomosaic, and we try to map different classes in the data set, such as we can see here, background, lake, and man-made features. And to make the problem more interesting, we also say that we want our UAV to focus on mapping the man-made features here, such as the building and the parking lot. So once it has discovered, we would want targeted exploration to focus on collecting more measurements there using an adaptive approach. So here are some of the similar plots that we saw earlier for this particular problem. So we compared targeted and non-targeted versions of our approach against two complete coverage patterns at different altitudes. And these plots show, again, how the map uncertainty and error evolve over the time. And again, as before, we can see that our approach succeeds in reducing uncertainty faster. But not only that, we also demonstrate that our planner can actually adaptively focus on mapping these areas of interest. So in this case, the class of man-made features. And this tells us that using an adaptive approach, we can focus on mapping these areas of interest much quicker, which is very relevant for any scenario where we want to find more information about an area, such as finding anomalies on the field. And finally, towards the end of my PhD, the complete system was deployed in an agricultural monitoring scenario in a European project, Flourish. So we demonstrated using outdoor vision-based state estimation to run the whole algorithm online and onboard the robot. So here we were mapping the excess green index metric from the images received from the UAV camera. So here's a short video of the experiments, just so that we can see that the UAV moves around to explore the space and also stops briefly to replan, making its own decisions online. And these plots show how the field map evolves as new measurements are collected. So on the color map, it signifies levels of excess green index, where yellower shades correspond to areas of higher vegetation. On the graph on the right, we can see a plot of how uncertainty decreases with the number of registered images, which is very intuitive because, as expected, the map becomes more complete over time, as we can see on the left side. So in particular, we can see from the final maps that the UAV successfully detects the less green soil and crop region in the center of the field, and the greener weed regions towards its edges, which is how we actually structure the field in real life. So that brings us to the last part of the talk, where we try to zoom out again to the big picture and see how these ideas and the potential of autonomous agricultural robotics actually, where would the future take us? So I want to highlight some of the points that we would like to address and some of the exciting opportunities that lie in this field. So first, one thing that we mentioned is how do we develop reliable sensor models for planning? So this is very important because in order to make decisions, we need to forecast what would be the most promising actions for the robot. And for this, we rely on the sensor model, which we specify based on how the sensor behaves in real life. So going back to the example of weed detection to make this more concrete, here we can see some examples of images that were classified using the crop weed classification model. And unfortunately, some parts of the image on the right are incorrectly classified. So the algorithm has mistaken some crops as being weeds. So the idea behind sensor models is, can we perform some analysis that tells us that our model is uncertain in its accuracy in these regions? Because if so, this would allow us to guide the robot on how it should behave in the future and its future plans. And another and very exciting and natural direction that research is likely to take is considering multi-robot applications. And that would include considering different sensors, but also different actions that the robots can perform. For example, if we were to use the UAV in order to inform the ground robot that weeding actions should be taken in a particular place, how do we go about coordinating behavior that's heterogeneous in the platforms, in the sensors, and in the actions? And we can think about many exciting scenarios here. For example, even equipping the UAV with for example, a sprayer that can spray fertilizer or pesticide in very targeted areas without the human actually making these decisions for the robot. And finally, a recurring theme in this talk has been scalability. So if we add these fancy things such as new sensors and new actions and consider bigger fields, how can we design algorithms that are actually scalable and useful? Because we want to be able to run them on board our robots as well. And one would hope that with also the recent technological advances would support work in this area as well. Because already, since a few years back, we're seeing new methods and new tools that we can use for our robots so that we can enable more scalable operation. And by addressing these issues, our ultimate goal is to really go up in the spectrum of robot autonomy and bring new paradigms to agricultural robotics. So that brings us to the end of this talk. Just to quickly recap, the focus of our research group here in FINOROB is autonomous and active decision-making, which incorporates different research themes, such as environmental mapping, informative path planning, and sensor modeling. Specifically in this talk, we look at some of the theory behind methods we can use to develop informative planning frameworks, focusing on UAV-based active sensing. But I think this is just the beginning, because there's many interesting avenues to explore in future work so that we can get really intelligent robots in agriculture rather than us telling them what to do. So thank you. That brings us to the conclusion, and I appreciate everybody that is listening.